M.G.Classes. Sharpen your thinking. Join us and feel the difference.
Hello viewers, my name is Kapil Bajaj and today I am here to bring a video which is based on the semiconductor and semiconductor devices. The purpose of uploading this video to understanding the basic concept of this chapter by doing the important questions. I feel that these questions may be useful for preparing the final examination of CBSE class 12 physics. So let us begin this video with the question number 1, and it's a basic fundamental question in which we have to check whether the given p-n junction diode can detect the different wavelength radiations. For example, here in the problem, the band gap, that is the energy gap between valence band and a conduction band for a p-n junction diode is equal to 3 electron volt, and we want to detect the two different wavelength radiations, one whose wavelength is 600 nanometer and another one is whose wavelength is 400 nanometer with the help of this diode. So what is the basic idea behind this problem? A p-n junction diode can detect the wavelength of the incident radiation only in those conditions when the energy gap of the diode should be less than the energy of the incident radiation. So first of all, let us calculate the energy of incident radiation. So for finding the energy of the incident radiation, which is obviously a photon, can be calculated by using the formula E equal to h into nu, where h stands for Planck's constant and nu is the frequency of incident radiation, which can be further expressed as c upon lambda. C means speed of light. So after substituting the values, for example, energy of the Planck's constant, I took 6.6 10 to the power minus 34. C, that is the velocity of a light in vacuum, 3 into 10 to the power 8, and lambda that is the wavelength of the incident radiation, which is in the first part equal to 600 nanometer or 610 to the power minus 9, and the value of this will come in the joule, and I express the energy in electron volt by dividing this 1.6 into 10 to the power minus 90, and after simplification I got the value 2.06 electron volt. So this is the first part. Similarly, we can calculate the energy of the incident radiation for the wavelength 400 nanometer, and its value after simplifying this all is coming 3.09 electron volt. So now we are in position to testify which one can be detected with the help of this p-n junction diode whose energy gap is given 3 electron volt. As far as concerned about the first radiation whose wavelength is 600 nanometer, its energy is coming 2.0 electron volt. Obviously, the energy of the incident photon is less than the energy gap of the diode. That is why the lambda equal to 600 nanometer radiation cannot be detected with the help of the diode whose energy gap is 3 electron volt. And for the wavelength 400 nanometer, the energy is coming 3.09 electron volt, which is above than the energy gap value. So we can see that lambda equal to 400 nanometer can be easily detected with the help of this p-n junction diode. So now here is a question number 2 in which it is given that the width of the depletion layer in p-n junction diode equal to 500 nanometer, and the value of the electric field of the p-n junction diode is equal to 5 into 10 to the power 5 volt per meter. And we want to determine the two things in this problem. Number one, height of the potential barrier. What is the height of the potential barrier? And number two, the kinetic energy of conduction electrons to diffuse the conduction electron from N side to the P side of the junction. So let us try to solve this problem by taking one by one part. So number one, in which we want to determine the height of the potential barrier of the p-n junction diode. So where height of the potential barrier of the p-n junction diode implies that we have to find out what is the barrier voltage of the p-n junction diode. So barrier voltage of the p-n junction diode we can calculate by using the formula, that is E into T, where E stands for electric field of the p-n junction diode and T is the thickness of the potential barrier or depletion layer, sorry. T is the thickness of the depletion layer. So putting the values, electric field is 5 into 10 to the power 5, thickness of the depletion layer is 500 into 10 to the power minus 9, and on simplifying this we get this value as a 25 into 10 to the power minus 2, which is further equal to 0.25 volts. So this is the value of the potential barrier. Second part of the question, to find the kinetic energy of the conduction electron which requires to diffuse them from N side to the P side of the p-n junction diode. So kinetic energy of the conduction electron is equal to the product of E into V naught. E, that is the charge on electron, and V naught is the barrier voltage. Charge on electron is 1.6 into 10 to the power minus 19 coulomb, and barrier voltage we have already calculated, which is coming 0.25. So when you simplify this, you will get the value of energy in terms of joule. But we want to express this answer in more convenient unit, that is electron volt. So therefore you can divide this value with 1.6 into 10 to the power minus 90, and on simplifying this you will get 0.25 electron volt as the kinetic energy of conduction electrons. Student, in the next question there is a circuit diagram as you can see in the figure. Resistor R whose value is V. So student, this is the next question in which a circuit diagram is given. As you can see, in the given problem, we need to determine the value of this unknown resistor which is connected in series across this p-n junction diode. The specification of this p-n junction diode are given as follows. For example, the maximum power rating of this p-n junction diode means this diode can consume this much power, which is equal to 100 milliwatt, and the voltage drop across this diode is given 0.5 volt. So we want to calculate the value of this R so that we can obtain the maximum current in the circuit. So first of all, let us begin for finding what is the actual voltage which is provided to this p-n junction diode. So the net voltage which is applied to this p-n junction diode can be calculated as the total voltage. Total voltage means the voltage of the circuit minus potential drop across this p-n junction diode. The voltage of the circuit is 1.5 minus potential drop of this p-n junction diode, which is equal to 1 volt. And after that, let us find out what amount of the current is flowing through this p-n junction diode. So as it is stated that the maximum power rating of this diode is 100 into 10 to the power minus 3 watt. So for this much amount of the power, the current that has to flow through this diode can be calculated power equal to voltage into current. So Power is 100 into 10 to the power minus 3, and the voltage of this diode 0.5 into current. So from here we get the maximum current 0.1 divided by 0.5, which is equal to 0.2 ampere. Current has to flow through the p-n junction diode when this is the rating of the power. So after knowing the value of this current, next step is to determine what is the value of this resistor. So resistor which is connected in series of this p-n junction diode according to the Ohm's law R equal to V upon I. So V is the net voltage given to this diode upon maximum current. So net voltage we have already calculated, that is 1 volt. So 1 divided by 0.2, and on simplifying this we get the value of this resistor as 5 ohm. Student, this is the circuit diagram for the next question. Here a 6 volt voltage along with a 20 ohm series resistor applied across the p-n junction diode, which is operating in the reverse mode, means reverse with a reverse biasing. So in the circuit diagram, according to this circuit diagram, we have to find out number one, current flowing in the circuit. Secondly, the potential difference across the p-n junction diode. And it is given that the drift current for the p-n junction diode is equal to 30 microampere. So student, for doing this question, first of all, I think we need to understand the characteristic of a p-n junction diode when it is operated with the reverse voltage. So we know that in case of a p-n junction diode, in the reverse mode or with the reverse voltage, the barrier voltage of the p-n junction diode is a very large, and as a result, a very small amount of the current flows in the p-n junction diode in the initial state. And this small amount of the current is called reverse leakage current, and it flows due to the minority carriers. But a stage comes when the breakdown of the p-n junction diode takes place, and at that voltage the current shoots up in the p-n junction diode, and this voltage is called breakdown voltage or Zener voltage. And at this voltage the p-n junction diode comes into the conducting state, means it allows the large amount of the current to flow through it. So when the diode will come into the conducting state, during that period the current will flow in the circuit. So it is given that the drift current for the diode is equal to 30 microampere. That means the conducting current by this diode is a 30 microampere. Since the conducting current by this diode is a 30 microampere, so same amount of the current will flow in the circuit. So conducting stage current is equal to 30 microampere, and that is the current flowing in the circuit. So in short, we can say that the current which is flowing in this circuit diagram is equal to 30 microampere, or 30 into 10 to the power minus 6 ampere. The second part of the question is to find what is the potential difference across the p-n junction diode. The potential difference across the p-n junction diode can be easily determined once we know what amount of the drop of the voltage is taking place across this 20 ohm resistor. So first of all, let us determine the potential drop across this 20 ohm resistor. So according to the Ohm's law, V equal to I into R, the current which is flowing in the circuit is 30 microampere, that is 30 into 10 to the power minus 6 into the value of this circuit resistor, that is 20 ohm. So on simplifying this, we get 6 into 10 to the power minus 4 volts. So this is the voltage drop across this 20 ohm resistor. After finding this voltage drop, we can find out the voltage potential drop or voltage across this p-n junction diode, which is equal to total voltage of this circuit 6 minus potential drop across this 20 ohm resistor, that is 6 minus 0.00006, and it is coming 5.9. So 5.9 volts is the potential difference across this p-n junction diode. These were the problems that I did solve for today. Next time I'll come with some more questions from the same chapter. Till then, goodbye and have a nice day.